Hello students, now we will study the angular momentum in case of a body rotating about a fixed axis. See the diagram where a particle P is rotating about a fixed z axis and its direction of linear velocity has been shown. Its position vector from C point at rotationary axis has been shown, and O is the point of origin, a reference point with respect to which we are discussing the rotationary motion of the particle P. So O is origin. Now in this case, as we know, the relation between linear and angular momentum is it is given by L equals to summation of product of vector Ri and vector Pi, where Ri is the position vector of a particle of a system or the body, and Pi is the linear momentum of that particle, and Li is the angular momentum of that particle, and L is the total angular momentum of that particle, of that body. So in this case, if the total angular momentum of all the particles are added, they have the same directions, so they are added vectorially, and finally we get this expression. We have already understood this thing. Now see here, for a single particle P, its angular momentum small l is equals to cross product of its position vector and its linear momentum, where we know R is denoted as the vector Cp, where R is denoted as the vector OP, which is equals to sum of vectors OC and Cp, where Cp is equals to vector R1. Since the momentum of the particle is equals to mass of the particle multiply its velocity, so the linear momentum of the particle is given by OP multiply mv, which further gives the vector sum of OC and Cp, and that cross multiplication by mv. So individually we can separate OC, its vector product with mv, plus Cp, its vector product with mv. So here are two terms or two components adding and giving the angular momentum of the particle P. Let us say this is equation number 1. In equation 1, the term Cp multiply mv provides the resultant direction parallel to z axis. means perpendicular to plane of rotation of particle. So the product Cp multiply Mv provides the relation R perpendicular multiply Mv in the direction of Z axis, which we are denoting by unit vector k cap, where V equals to omega R perpendicular. The R perpendicular is the straight distance of the particle P in its plane from the point C that we have shown in the figure by R1. So further, the relation can be rewritten as Cp cross Mv is equals to M R perpendicular square omega k cap. Since V equals to R perpendicular omega, that's why we have put it here. So the angular momentum of the particle P can be expressed as, again, L equals to L along Z axis plus OC multiply MB, where LZ equals to Cp multiply MB equals to M R perpendicular square omega in the direction kk. The direction of LZ is parallel to the rotationary axis, whereas the direction of OC and product of MV is different. So if we consider the complete particles of the body, in that case, for the system of I particles, we can write the total angular momentum of the body as L equals to sigma of Li, that gives us sigma of Lij plus sigma OCI multiply MVI, where I subscript denotes the individual particle, which can be further rewritten as L equals to sigma Lij plus sigma Li perpendicular, sigma Li perpendicular, where sigma Li perpendicular is equals to sigma of OCI multiply MVI. The direction of the product OCI and MVI is perpendicular to the rotationary axis. So further, the same equation can be rewritten as for angular momentum of the body, L equals to Lz plus L perpendicular. As we know from the above equation, we have written since Lz is equals to sigma of Mi Ri square omega k cap, which gives us the value I omega k cap, because I equals to sigma Mi Ri square and L perpendicular equals to sigma of OCI multiply Mi Vi. L equals to I omega k cap plus L perpendicular. The angular momentum which we have considered here is for a body which is rotating symmetrically about the rotationary axis, and in that case The change in the angular momentum along the z-axis is expressed as the torque applied on it. We know that d by dt of Lz is equals to d by dt of I omega k cap is equals to tau along the direction k cap. So if the net torque is 0, the change in the angular momentum is 0. So angular momentum parallel to the rotationary axis will be constant when external torque is 0 or external the torque is in equilibrium condition. The rotational motion is in equilibrium. So if tau is equals to 0, d upon dt of Lz is equals to also 0, and angular momentum along rotationary axis z axis here will be conserved. Yet when we are taking only the components of torque acting along direction of z axis, then we are considering that the torque is given by the magnitude of torque multiply unit vector k cap, and since the component of torque perpendicular to z axis are not considered, then the net angular momentum will be given by Lz, that is I omega k cap, that is equals to tau, where dLz by dt will provide us the value of torque, or it gives us d upon dt of I omega is equals to torque, which further provides us the value I alpha equals to tau, where alpha equals to d omega by dt. So this is the relation between angular acceleration, torque, the angular momentum. That's all for today. We will take the next topic in our next time. Then good day.